You know, for as long as we've been human, we've looked up at the stars and asked some pretty big questions. And today, we're diving headfirst into one of the biggest, our place in the cosmos. We're going to explore the amazing science of astrobiology and the search for a living universe.
And really, it all boils down to this one huge question, doesn't it? Are we alone? When you think about the hundreds of billions of stars just in our own galaxy, it almost feels impossible that we'd be the only ones here. But, as we're about to see, getting to the answer is way, way more complicated than you might think.
Because you see, before we can even start searching for life out there, we have to figure out what it is we're actually looking for. And that leads us to maybe the single biggest hurdle in all of astrobiology.
What even is life? I mean, seriously, it sounds so simple, but it's a question that has stumped the greatest minds for centuries. And the truth is, to this day, we still don't have one single definition that everyone agrees on. Every time we try to box it in, we run into these really cool, weird problems. So, let's say you define life by its metabolism. You know, it takes in energy, it grows, it makes more of itself. Well, guess what fits that description perfectly? Fire. It consumes fuel, it grows, it spreads. But we wouldn't call fire alive, right? Okay, so how about we define life by its ability to create order from chaos? Well, then you've got crystals. They grow in these beautiful, highly ordered structures, pulling order from a messy solution. But they're not alive either. It's a super slippery concept.
And this suggests maybe we're thinking about it all wrong. As these researchers, Cleland and Sheba, pointed out, think about water. Before we knew about atoms, all we could do was describe it. It's wet, it's clear, you can drink it. But once we had the theory of atoms, bam, we could say with total certainty water is H2O. What we might need for life isn't a better definition. It's a whole new scientific theory of what a living system even is.
So without that big, grand theory, astrobiologists have to be practical. If you can't search for every weird and wonderful kind of life you can imagine, what do? You focus on what you know. You search for life as we know it, and that gives them a concrete shopping list of things to look for.
And this recipe, it's actually pretty straightforward. It's got 3 key ingredients. Number 1, liquid water. It's called the universal solvent for a reason. It's the perfect place for all the messy chemistry of life to happen. It's why NASA's whole strategy is basically follow the water. Number 2, the right building blocks. You need stuff like carbon, which is an absolute superstar at forming the long, complex molecules life needs. And number 3, you need a source of energy. It could be light from a star like our sun, or it could be chemical energy from the environment.
Okay, so we've got our recipe. Now the fun part begins. Where do we go looking? We can start scouting the cosmic real estate, starting with the biggest scale imaginable.
So it turns out not all parts of the galaxy are created equal. Think of it like cosmic real estate. Location, location, location. If you look at this chart, you'll see that near the chaotic center of the galaxy, you've got a ton of heavy elements, which is great for making planets, but it's also incredibly dangerous. It's just bombarded with radiation from things like supernovas. If you go too far out to the edges, it's safer, but there's not enough raw material to build planets in the first place. So there's this Goldilocks zone, this perfect cosmic suburb that's just right. And guess what? That's exactly where we are.
But let's bring it closer to home, right into our own backyard, because we've got some amazing candidates. Of course, there's Mars, which we now know was once warm and wet, and we keep getting these mysterious whiffs of methane gas, which on Earth is mostly made by living things. Then there's Jupiter's moon Europa. It's covered in ice, but underneath, there's almost certainly a huge, salty, liquid water ocean, with twice the amount of water of all of Earth's oceans combined. Just think about that. And then you have Titan, Saturn's moon. It's a totally alien world, where it rains liquid methane. Could some completely different kind of life exist there? It's an incredible thought.
All right, so finding microbes would be incredible, a total game changer. But let's be honest, what we're all really hoping for is intelligence, right? And this brings us to one of the fiercest debates in science. Was something like us a total 1 in a trillion fluke, or is intelligence something that evolution is bound to produce sooner or later?
This whole puzzle is captured perfectly in this one simple question from the physicist Enrico Fermi. He was basically saying, look, the universe is ancient. The galaxy is huge. If intelligent life is common, there should be civilizations out there that are millions, maybe billions of years older than us. They've had more than enough time to get here, or at least send a signal, so where is everybody? That question, that incredible, deafening silence, that's the Fermi paradox.
So how do we explain it? Well, there are 2 big ideas clashing here. On one side, you have contingency. This is the idea that we are just a cosmic accident, a long, improbable chain of lucky breaks. If you could rewind the tape of life on Earth and play it again, you'd get a totally different result, and it almost certainly wouldn't be us. But on the other side, you have convergence. This argument says that evolution tends to find the same good ideas over and over again. Things like eyes or wings for flying have evolved independently multiple times. So, if intelligence is such a powerful survival tool, why wouldn't it pop up again and again too?
And you know what's crazy? We can see this debate playing out right here on our own planet. This chart shows something called the encephalization quotient, or EQ. It's basically a measure of how big an animal's brain is compared to its body size. No surprise, we're at the top. But look at this. Dolphins. Their EQ is 4.6. That's actually higher than our own ancient ancestor Homo habilis. Our last common ancestor with a dolphin was like 90 million years ago. That's a powerful piece of evidence that high intelligence isn't just a one-time fluke.
But what if the whole debate we've been having is based on a flawed assumption? What if we're looking for the wrong kind of intelligence altogether? Our entire search is geared towards finding beings like us, but our own technology hints that any advanced species might look very, very different.
We all know about Moore's law, right? The idea that computing power doubles about every 2 years. Well, check this out. Our ability to read and write DNA, the literal source code of life itself, is advancing even faster than Moore's law. We are gaining the ability to engineer biology itself.
And that leads to this absolutely wild idea. What if the amount of time a species is both smart enough to build radio telescopes and still stuck in its original messy biological body is just incredibly, incredibly short? Maybe just a few thousand years. On a cosmic timescale, that's nothing. It's the blink of an eye. The very thing we're searching for might be one of the rarest, most fleeting phases of a civilization's existence.
And so, this brings us to one final, mind-bending thought that just changes the entire game. We're spending all this time and energy scanning the skies for biological beings, for life as we know it. But if any civilization is advanced enough for us to find, they're probably way, way older than we are. So maybe the real question isn't just, are we alone? It's something else entirely. If we do find someone else out there, are they even going to be biological at all?